Hello everyone, so welcome to the tutorial sessions. So today we are having our first tutorial 1. So the purpose of this video lecture is to help you to find solutions of some of the problems that I have already shared with you. So we start with the problem number or question number 1 and 2 together. The question was, draw qualitative graph plots for concentration time for zero order reaction. This was question 1, and for the non-zero order reaction it was question number 2. So we assume that A is going to be, and this is the concentration versus time plot. So I would start with for the zero order reaction here, and our initial concentration we will assume an A naught over here, and so we can see that it shares a linear relationship with time t, and this is A naught. So of course the concentration would change with time following a straight line with a negative slope. But here for a non-zero order reaction, since it depends on some power of the concerned concentration, so if we have this thing as A naught, so obviously it would have an exponential decay. Alright, and if I want to draw the curve for the product, so this is the reactance. So if you want to draw the curve for the product for non-zero order, so it will go like this, and for the zero order reaction, obviously it will be a straight line passing through the origin. Okay, so let's move on to our question number 3. So question number 2 was, this reaction was given, and this is a single state reaction, and you are supposed to find minus dV dt. So at the beginning I discussed that for a stoichiometric reaction like this, rate is expressed is equal to minus 1 over alpha dA dt is equal to plus 1 over gamma dc dt. So all the coefficients, stoichiometric coefficient would appear in the rate expressions. So therefore, let's do this for here. So rate is equal to minus 1 by 2 dB dt is equal to dB2 dt. So this is plus 1 over 1, which is 1. So this would become equal to rate constant K B whole square, because here it says single state, that means the coefficient can be assumed as the molecularity, so we can regard it as a second order reaction. So we can simply write it like that, or therefore finally we were supposed to find minus dB dt, so that becomes equal to twice of K B square. Okay. Alright, so let's move to the next. So question number 4 asks you to find out the dimension for the rate constant for half order reaction. So for this type of question, what we do, we actually derive a generalized expression. So rate is equal to this, and from there we express K is equal to rate divided by concentration to the power n. And then we put the correct dimension of the rate, so moles per liter per second divided by moles per liter whole to the power n. And then it comes down to a general expression like this. So then for n is equal to half, we can have this final answer, and that also corresponds to the molarity. So the uppercase m to the power 1 minus n to the power s minus 1. So that is the generalized expression for this one. And for n is equal to half, this is the particular answer. So you can verify this as well by putting n is equal to 0, n is equal to 1, and here or here, and n is equal to 2, etc. To verify that the dimension is coming to the already derived dimension for the rate constants that we have got it during our lectures. Okay, so next we move on to the question number 5. So question 5 contains a numerical problem. It says how much of 10 gram of radioactive copper will be left after 6 hours in the following radioactive decay. So copper 64 is getting decayed into zinc 64 with emission of a beta particle, and is given that the half-life is 12.8 hours. So of course we would assume that the radioactive decay follows the first order kinetics. So therefore, according to the first order rate law, this is the valid equation. NT over N naught is equal to U to the power lambda T, and where the symbols refer to the usual quantities. So, or in our case, NT is unknown, and we started with 10 grams of radioactive copper, that means N naught is 10, is equal to E to the power lambda multiplied by 6 hours, so T is equal to 6. And how to find lambda? So there is a relationship of lambda is equal to 0.693. So T half. So T half is 12.8 hours. Okay. So if we put that, we get the lambda value in our inverse. Okay. So if we put the lambda value over here, and if we try to solve NT, we should be getting this answer 7.26 gram. Okay. So you can do it yourself and please verify whether you are getting the correct answer. So next we go to the question number 6. So question number 6 is again a numerical problem where it says that a gas is being decomposed and the order is 3 by 2, and 84% of the gas got decomposed in 2 hours of time, and initial pressure of the gas was 1 atmosphere. So whenever this type of problem is there, we must assume that the reaction going on in a closed container, so the pressure of the gas is basically the measure of the concentration of the gas. So we would treat the initial pressure of 1 atmosphere as the initial concentration. So therefore, since it is a 3 by 2 order reaction, and we would treat this reaction as in terms of disappearance of the reactant, that is the gas itself. So minus dAdt is equal to K A to the power 3 by 2. Okay, so here, or we have to go like this, minus dA A to the power 3 by 2 is equal to K dt. Okay, so now we have to integrate that, but remember, while we integrate, so at T is equal to 0, our pressure of the gas was 1 atmosphere, and the question says that find out the rate constant. Okay, so the question is find the rate constant K. Okay, so at time T is equal to 0, pressure was 1 atmosphere, and at time T is equal to 2 hour, so here it says 84% of gas is decomposed. So here is the trick. So 16% of the gas remains. So whenever we talk in the term of reactant, so 16% of 1 atmospheric pressure is still left. So that means at T is equal to 2 hour, the pressure of A should be 0.16 atmosphere, because 84% or 0.84 atmosphere of the gas has already been decomposed. So therefore, if we integrate that, so finally your answer, that means the rate constant, should come 1.5, but this is the numerical value. Now you have to put the correct unit. Without the correct unit, your answer would be wrong. Okay, so the correct answer here, make minus 1, sorry. So the correct answer is 1.5 atmosphere to the power minus half multiplied by hour to the power minus 1, or hour inverse. So that's the rate dimension of the rate constant for a 3 by 2 order reaction. Alright, so next we move to question number 7. So question number 7 was almost similar to the question number 6. So there was a substance A, hydrogen peroxide, getting decomposed following a first order kinetics. So N is equal to 1. Rate constant is given. It asks you to find the time to complete 1/3 of the reaction. Okay. So since this is the first order kinetics, we have to write that integrated rate law. So we can write it like this. Natural log of A naught divided by AT is equal to KT. Now it says find the time to complete 1/3 of the reaction. So that means what if the reaction proceeds 1/3 of the gas has been decomposed, or 1/3 of A has been decomposed. That means 2/3 is still left. So therefore that was the only trick. So in terms of AT, we have to plot 2/3 of A naught is equal to KT, or a natural log of 3/2 is equal to KT. And therefore, if we put the value of K is equal to 3 multiplied by 10 to the power minus 2 made inverse, we should be getting the value T is equal to somewhere like 16.9 minutes, something like this. So please verify this answer from this equation. Okay. So next we go to question number 8. So the next question deals with the method of initial rate. So there are 3 reaction trials have been there, and these are the initial rate of A naught and B naught, and this is in the form of K, A to the power A multiplied by B to the power B. And so these are the rates with appropriate units, and I'm not writing the units here because I'm just interested to know what is the value of A and B. So the question says find A and B. So if you look at the trials, you see that whenever B naught becomes double from 0.1 to 0.2, the rate is almost the same. So therefore, immediately we can confer that B is equal to 0. So this is 0 order with respect to B. So now let's come to A. So we will select these 2 trials where the concentration of B is constant. So therefore, we go for the trial number 2, that is we call it R2 is equal to 6.14 is equal to whatever the rate constant K and 0.15 to the power A, and R1 is equal to 2.73 is equal to K multiplied by 0.1 to the power A. Okay, and this B to the power 0 is equal to 1, so we are not writing that. Now what we're going to do is we take R2 divided by R1. So if we do R2 divided by R1, so therefore we have this 6.14 divided by 2.73, so we can go like this, is equal to, so these 2 cancel out, and we have basically 1.5 to the power of A. Alright, so now we are going to find out A. So basically natural log of 6.14 divided by 2.73 is equal to A multiplied by natural log of 1.5. So therefore here we can write that A is equal to bottom I have ln 1.5, and at the top we have the natural log of 6.14 divided by 2.73. Okay, and now we should expect to solve it and try to find the order. Okay, so if you do so, please make sure that you take the near about or the nearest whole number, and it will come very close to 2 or approximately 2. Okay, and we can take this approximation safely because it will come very close to 2. So you please check it out and verify whether this answer is true. Okay, so next is question number 9. So question number 9 is a very straightforward problem. This is the second order reaction, A going to B. The rate constant is given. The initial concentration A naught is also given. And you have been asked to find out AT, where T is equal to 20 minutes. So therefore, we can use this expression, that is 1 over AT is equal to 1 over A naught plus KT. So here you see A naught is given, K is given, T is given. You have been asked to find out AT, the concentration of time, concentration of A at time T. All right. So just one comment over here, that in exam, if numerical problems are given, then depending on the marks, you have to choose which way you have to solve. That means if it is a very short objective type question, 1 or 2 marks, you can directly use this formula. Or if you see that it has been given like 3 or 4 or 5 marks, so it's better to deduce this formula from the basic rate equation, that is minus dAdt is equal to K A square. All right. So now we move to question number 10. So question number 10 deals with the second order reaction. So this is given. So this looks like hydrolysis of an ester in basic medium. Anyway, that doesn't matter. So the initial concentration of A and B, here the B can be treated as OH minus, no problem, has been 0.002 mole M and 0.3 moles per liter, respectively. So the question says that if it takes 30 seconds for 1% of A to react, find K. So we would proceed the reaction with like this. So A plus OH minus is equal to some products. At time t is equal to 0, the initial concentration of A is A and OH minus is B, and the product is 0. And at time t is equal to whatever, 30 seconds, we have A minus X, we have B minus X, and the product is X. So if you look at this scenario, and you see X is given, because X here is actually, it says it takes 30 seconds for 1% of A to react. Okay, so 1% of A to react means we can easily guess about X. Okay, so now what we can do is we can derive the rate law. Okay, once again, depending on the marks, if it is the objective type question, then you don't need to derive, you can directly write to the formula. But I believe whenever these problems come, it won't be an objective type question, but it may have some major marks like 5 or 6, and you have to derive this rate equation for second order. And therefore, if you derive that, obviously you will get something like this: 2.303 divided by A minus B multiplied by log base 10 B multiplied by A minus X over A B minus X is equal to KT. Okay, so in this expression, B is there, okay, and A is given, and T is 30 seconds, and X is given, like it says that 1% of A to react. So you have to exactly find out what is X. So should you take X as 0.1 or should you take X as 0.99? So you can check it out. So it's up to you. And then finally you have to find out the rate constant K. So I'm not giving you any answer for this one. So it's for you to try, and you check the answers with your fellow classmates to see whether you have got the correct answer. So it's a straightforward problem. So next we move on to the question number 11. So question number 11, some reaction is given, and it says that it is a first order reaction. The rate constant is given. And the question is, you have to calculate the time required for the total pressure to rise from initial pressure of 0.1 atmosphere to 0.15 atmosphere. So that means it says the initial pressure was 0.1 atmosphere, and what is the time required to reach the total means what is the time required for the total pressure to reach 0.15 atmosphere. So remember, the question is the total pressure of the system containing A, and of course B and C, everything. And it has a second part. The second part says find the total pressure after 100 seconds. Okay, so the thing is, if you recognize, so the hint is, if you recognize that this is a first order reaction and the concentration, the pressure are nothing but can be treated as the concentration, then you can easily solve this problem. The hint is the pressure is to be treated as concentration terms. Okay, and then you can, go for it. So at time t is equal to 0, we have the initial concentration A, and this is 0 and this is 0. And at time t is equal to, okay, so time t is equal to t, so that we need to find out at time t is equal to t, the initial pressure total pressure becomes 0.15 atmosphere, and at that point you have to calculate what's happening in the system. So A minus x or 2x at time t is equal to t. Here we have 4x, x, etc. So you have to frame a simple algebraic equation, and you have to find the value of x, and then only you will be able to find the total pressure, and from that you can easily solve the rest of the problems. So that is the hint. You have to try it out. So I'm not giving you the answer yet. So please try it out and verify whether all of you come to the same answer. Okay. And we had one more problem left in this tutorial, that was question number 12. But the question deals with a chain reaction, free radical chain reaction, and it contains the Bodenstein mechanism of formation of HBr. So during the lecture, I told you that you have to derive the integrated rate law for the HBr formation, and to help you, I think in the next tutorial I would try to provide you a solution that how to approach that chain reaction to obtain an expression for the rate of formation of HBr. And then the actual question of question number 12 deals with the final answer. Okay, so there is one more part to it. I will also explain that, but before that I will help you to reach the statement of the question, that is the expression for dHBr dt, and that problem would require some amount of time and some amount of derivation on the board. So I'm not dealing it here today. So we will try that in the next tutorial, where we will deal problems especially from the simultaneous reaction part. Okay, so you please practice these problems yourself, and I will see you in our next video lecture session. So till then, goodbye.